Some of the biggest mysteries in the universe are all about other questions, like the question, what is it?
A glowing object is tearing through our solar system at over 130,000 miles per hour. And it's not from here. Scientists confirmed it's interstellar. But what they've discovered inside this comet? That's where things get weird.
There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe. While many think it's just a comet, some theorizing a possible alien origin.
First, it started venting carbon dioxide like no other comet. Then, it revealed glowing nickel lines, but no iron. And when you hear what some are claiming that means, you won't believe the theories exploding online. This thing isn't just real, it's interstellar. On July 1st, 2025, a telescope in Rio Hurtado, Chile, locked eyes on something streaking across space. The Atlas survey system flagged it, an object now officially known as Comet 3I/Atlas, and it's the third ever confirmed object from beyond our solar system, after Oumuamua and 2I/Borisov. But this one? It's glowing, it's venting, it's alive. Unlike the rocky mystery of Oumuamua or the icy fireball of Borisov, 3I/ATLAS comes in with a full coma, a thick cloud of dust and gas, and a speed that makes Earth's orbit look like a parking lot. Roughly 137,000 miles per hour on a hyperbolic trajectory that proves it's not tied to our sun's gravity. It's in, it's out, no return. Closest approach to Earth, about 1.8 astronomical units. That's over 170 million miles away. Closest approach to the sun, October 30th, right inside Mars's orbit. The kicker? It's arriving from the direction of Sagittarius, right toward the center of the Milky Way. Galactic vibes? Strong. And yes, you saw the rainbow-colored photo. But that viral image? It's a composite from Gemini North using different filters. The comet doesn't literally glow like a skittle, but the teardrop-shaped dust cocoon around the nucleus is absolutely real and caught the attention of Hubble, Webb, and more. Right now, they're all watching. Because this thing isn't just rare, it's talking. And next, it tells us what it's made of. Hard data on its chemistry, CO2-dominated coma. Within weeks of discovery, the James Webb Space Telescope swung NYRSPEC toward 3I/ATLAS, and the verdict landed hard. The coma is carbon dioxide dominated, not a whisper, loud. The carbon dioxide to water mixing ratio clocks in at about 8:1, among the highest ever seen at this distance. Webb also spotted water vapor, carbon monoxide, carbonyl sulfide, water ice, and dust, plus a telltale boost in outgassing on the sunward side. That is classic comet behavior, measured with 21st century precision. Why this turns heads? Most comets we know go water first as they warm, but at about 3.3 astronomical units. Water is sluggish, while carbon dioxide is ready to run. A carbon dioxide-heavy coma out here hints that 3I/ATLAS either formed near a carbon dioxide ice line in its birth disk or had its surface processed by radiation in ways unlike many hometown comets. Those are testable ideas as the comet brightens toward perihelion and then cools on the way out. Also, a key tools note. Carbon dioxide is notoriously hard to study from the ground because Earth's atmosphere soaks up the crucial infrared bands. That is why space observatories like Webb are game changers. They can separate the drivers of activity, molecule by molecule, instead of guessing from proxies. And let's kill one myth while we are here. Carbon dioxide rich does not mean unnatural. Carbon dioxide, water, carbon monoxide, and sulfur species are standard comet volatiles. What is unusual is the ratio, not the molecules. So we know it is venting, we know what is leading, and we know the engine wakes up early. But chemistry is only half the plot. The spectra also flashed a metal twist that lit up the rumor mill. Metals seen so far, nickel lines with no iron lines yet. When astronomers turned the ESO Very Large Telescope using UVES and X-Shooter on 3I/ATLAS, they caught a forest of neutral nickel lines in the near ultraviolet, roughly 3,400 to 3,600 angstroms. Meanwhile, the usual neutral iron lines? Not there yet in those same exposures. As the comet crept sunward, the textbook cyanide band near 3,880 angstroms flicked on, a clean sign that volatile release was ramping. One observing campaign even pinned down production rates. Log Q of cyanide about 23.6 per second, and log Q of nickel about 22.7 per second, at a heliocentric distance of about 2.85 astronomical units. Translation: active comet, real numbers, nickel lighting up first. Context matters. Back in 2021, during 2I/Borisov, researchers also found gaseous nickel around 2.3 astronomical units, likely fed by a short-lived nickel-bearing parent molecule that breaks apart and seeds the coma. No blast furnace needed. Around the same time, a broader survey showed iron and nickel can appear even far from the sun, overturning the old heavy metals only near perihelion idea. So why nickel without iron here? Could be chemistry, different parent molecules, could be excitation and line strengths, could be dust release physics favoring nickel carriers first, or simply sensitivity and timing. Iron may be present but below the detection limit, for now. That's the game as we head toward perihelion in late October. Keep repointing the telescopes. If iron lines emerge, we tighten the nickel-to-iron ratio and refine models. If they stay elusive, that becomes the clue. The spin, the jets, and the breakup watch. But how do you tell what interstellar comets like 3I/Atlas are really made of? You track its spin, map its jets, and keep a respectful eye on the breakup watch. First, the spin. Comets don't just glow, they pulse. As the nucleus rotates, sunlit vents turn on and off, making the brightness rise and fall in a repeating rhythm called a light curve. Catch that rhythm, and you get the rotation period, plus hints about shape, lumpy potato, elongated shard, or something in between. If the pulse changes over time, that's a tell that outgassing jets are actually torquing the comet, speeding or slowing the spin like a tiny thruster. Now the jets. Think of them as frosted geysers, narrow fans of gas and dust that sweep around with the nucleus. In deep images, those fans can draw corkscrew patterns through the coma. Match the pattern to the pulse, and you can pin the vents, estimate how active they are, and figure out which gases are doing the pushing. Tie that to the nickel story, and you might learn which grains are releasing metals and when. Then there's the breakup watch. Some comets spin themselves into trouble. Venting adds torque. Torque raises stress. Add thermal cracking, and a nucleus can shed fragments or even split. If that happens, the light curve stutters. The coma gets weirdly lopsided, and new mini-tails appear. It's dramatic, but it is also a science jackpot, because fresh breaks expose interior ice that sunlight hasn't cooked. One more thing. Tracking jets lets astronomers separate normal non-gravitational nudges from anything truly odd. If tiny coarse tweaks line up with gas activity, that is comet physics. If they persisted without gas, that would be a different conversation. X-rays, tail snap-offs, and the solar wind lie detector. Those jets you just tracked, they do more than spin the comet. They feed the plasma, and that is where the sun starts writing its signature across three I/ATLAS in high-energy ink. Here's the play. The solar wind is a river of charged particles streaming off the sun. When that fast stream slams into a comet's neutral gas, it rips electrons away in a process called charge exchange. The payoff is wild. The coma lights up in X-rays. Think of it as a cometary aurora, except the canvas is a drifting cloud of carbon dioxide, water, and dust. Point an X-ray telescope at the scene and you can literally map where the wind is biting, how fast it is blowing, and what ions are doing the punching. Why does that matter here? Because a carbon dioxide-heavy comet changes the script. Different neutrals mean different X-ray fingerprints and different brightness timing as activity ramps. Catch those changes and you are not just confirming outgassing, you are diagnosing the engine that drives it. Now for the drama you can watch from Earth, tail disconnection events. When the interplanetary magnetic field flips or a solar storm sweeps through, a comet's ion tail can sever like a ribbon snapped by a gust. One moment, the tail is a clean lance pointing away from the sun. The next, the outer segment detaches and drifts, while a fresh tail regrows from the nucleus. And here's the kicker. This is the lie detector for bad takes. If the comet's path or tail angle twitches in sync with solar wind hits and magnetic flips, that is textbook plasma physics. Not steering, not thrusters, not a covert course change. Pair the X-ray glow, the tail snap-offs, and the jet timing with the light curve from the last subtopic, and you get a full-stack readout of when, where, and why 3I/ATLAS moves the way it does. The color game. Why green, why red, why it matters. If you've scrolled through comet photos online, you've seen it. Those glowing shades of green, red, even blue streaks in the tails. With 3I/ATLAS, the color show is more than just pretty. It's a diagnostic tool, a cosmic code scientists can read. Take the recent reports of a green halo. That glow usually comes from diatomic carbon, C2, fluorescing in sunlight. It's a fragile molecule. It doesn't last long before breaking apart, so when you see it, you know it's being created fresh and close to the comet's surface. That tells astronomers exactly which gases are driving the show and where the action is hottest. But color isn't static. As 3I/ATLAS gets closer to the sun, expect the spectrum to shift. Dust scattering sunlight can throw golden or reddish tones. Sodium atoms, if released, can give off a deep amber glow. Meanwhile, the ion tail, made of charged particles swept by the solar wind, often glows blue, especially when dominated by carbon monoxide ions. Put that together, and the comet isn't just glowing, it's broadcasting its chemistry in full color. Why does this matter? Because subtle color differences can flag big science questions. Is 3I/ATLAS releasing more carbon than expected? Is radiation breaking down grains faster than in solar system comets? Does the green fade unusually quickly, hinting at a unique surface layer? Every hue is a clue. And here's where myths creep in. Some posts equate green comets with doom, calling them toxic or dangerous. But in truth, those glowing molecules are short-lived and harmless at Earth's distance. The color game isn't a warning. It's a lab test written across millions of miles of space. Polarized light. Dust fingerprints you can't fake. Now let's twist the light and squeeze out texture. When sunlight bounces off a comet's dust, it doesn't just change hue, it gets polarized. Measure that polarization, and you're suddenly reading the dust's size, fluffiness, and makeup like a passport stamp. Here's the move. Astronomers track how polarization rises and falls as the phase angle changes, the angle between the sun, the comet, and us. Different dust gives different curves. Fluffy, porous aggregates push polarization higher. Compact, glassy grains mute it. Even the famous negative branch at very small angles, the brief dip below zero, tells you the grains are complex, not smooth marbles. In short, polarization is the lie detector for pretty pictures. It turns a photo into physics. Why this is spicy for 3I/ATLAS. A carbon dioxide-heavy comet with quirky metals behavior might be lofting lighter, more fragile grains early, then tougher, darker stuff later. If the nickel shows up before iron because certain grains break apart faster, the polarimetric curve should shift as the jets evolve. Catch that shift, and you connect color, chemistry, and grain physics into one story. What's venting? Which grains carry it? And how sunlight sculpts the flow. Bonus? Polarimetry is brutal on hype. If someone claims shiny panels or polished alloy shards, the polarization says otherwise. Metallic, mirror-like surfaces would tank the comet-typical curve. What we expect, and so far see in normal comets, is a signature of dusty, irregular, carbon and silicate-rich grains. If 3I/ATLAS follows that same pattern, it strengthens the natural comet verdict while still letting us spot real anomalies if they appear. And the best part? Polarization changes with time. As vents switch on, angles shift, and the comet rolls toward and past perihelion, that curve is going to breathe. Link those breaths to the jet timetable, and you've got a living diagnostic of dust factories across the surface. Ready to go deeper? Because once you can feel the dust, the next question is how the seasons on this interstellar wanderer turn the jets on and the radio and radar playbook. Hearing the comet breathe. Radio and sub-millimeter waves turn 3I/ATLAS from a pretty glow into a breathing organism you can measure. First up, the 18-centimeter line of hydroxyl. Sunlight breaks water into hydroxyl and hydrogen, and those hydroxyl molecules can maser, amplify radio waves, right in the coma. Track that whisper and you get a direct proxy for water release hour by hour. If a jet turns on, the hydroxyl line brightens. If a vent sleeps, it fades. Slide to millimeter and sub-millimeter bands, and the score gets richer. Carbon monoxide, hydrogen cyanide, methanol, each sings at its own frequency. With arrays like ALMA, you can map those lines across the coma, measure outflow speeds from the line shapes, and even spot rotating jets as the line peaks swing in sync with the spin period. Put that next to the polarization and color work, and the pieces click. Which gases drive which jets, and how dust tags along for the ride. Now, radar. When comets pass close, planetary radars can ping the nucleus and read the echo, revealing size, shape, and surface roughness. For 3I/ATLAS, the pass is too distant for a clean radar image, but the method matters. Radar is the reality check that tells you whether a nucleus is a smooth pebble, a lumpy contact binary, or a rubble pile covered in frost. File it under "not this time," but this is how you'd do it. Here is the hook. Radio lines are truth-telling in a way images cannot be. They give you temperatures, densities, velocities, and production rates with timestamps. If a solar storm snaps the ion tail, radiochemistry logs the hit. If seasonal tilt hands the sun to a new hemisphere, the line ratios pivot on cue. What has changed recently? Activity and tail growth. Here's the evolving and very camera-ready part of the story. As sunlight increases, 3I/Atlas is activating, just like a textbook comet. In late August, a student scientist team using Gemini South in Chile captured a brand new lengthening tail using the GMOS instrument. The official release from NOIR Lab shows a crisp streak of dust flaring off the coma as gas and particles stream away. Shortly after, AP News picked up the story, noting that both the tail and surrounding coma are expanding rapidly as the comet heads toward its late October perihelion, and reassured readers there's zero threat to Earth. Even earlier, in July, Hubble's imagery had already revealed a teardrop-shaped dust cocoon and helped estimate the size of the nucleus, giving astronomers a detailed before snapshot. By late summer, the aftershot made it clear. The comet was switching on, and fast. Here's where it gets even more intriguing. During the September 15th lunar eclipse, deep sky images from Namibia captured 3I/ATLAS glowing green. That glow is likely from diatomic carbon, C2, fluorescing under sunlight, a well-known signature in comet science. But only weeks before, some reports noted that the comet was surprisingly poor in carbon chain molecules. That contrast, green glow now, carbon chain poor then, underscores just how rapidly comet chemistry can evolve with changing light and geometry. As the tail lengthened, some posts claimed the tail's angle was a course change, or that the comet was aiming at Earth. Let's clear that up. Comet tails always point away from the sun, shaped by solar radiation and the solar wind. The ion tail is a straight streamer, pointing directly away from the sun. The dust tail curves more gently along the orbital path. And sometimes, perspective tricks the eye. In certain views, it can even look like the tail is pointing toward the sun, a visual illusion known as an antitail. But again, that's just geometry, not steering. Expect the activity to continue ramping up through late October as the comet dips to perihelion. It'll briefly disappear behind the sun from Earth's perspective, then re-emerge in early December. Everything we're seeing, the heating, the tail, the gas venting, is exactly what comet physics predicts.